I guess you can all hear me. Can you hear me? Hello? Can you hear me? Can you hear me? Oifweme Friday. Adam Ahmed, can you unmute and talk to me? Can you hear me? Can you hear me? Please unmute yourself if you can hear me and say something. Oifweme Friday, you should be able to hear me.
Yes, we can hear you, sir.
Yeah, that's Adam Ahmed.
Yes, Adam Ahmed Muhammad, yeah, from Maiduguri.
Yeah, you're welcome to this class. Oifweme Friday, you should be able to hear me because you're not muted. Also,
Yeah, now we can hear you, sir. Go ahead.
yes, I want others. You can hear me. Chabong
Yeah.
Nantip, can you please unmute yourself and you can. Okay, that's who is Ifi Josh? That's Oifweme Friday, right? Okay, Ifi Josh said you can hear me. Good. What about Olanre, Rachel Olanre, can you hear me? Rachel Olanre Waju, can you please unmute yourself? Chabong, if you can hear me, can you just wave your hand? Okay, you can unmute. You can talk. Just go to the mute button, unmute yourself and talk. I want to hear you speak. Unmute, the mute is by your left hand.
I have unmuted myself, sir.
Okay. Can you hear me, sir?
Yes, I can. That's Rachel
Okay.
Olariwaju, right?
Yes.
I also had Chebong Namtip.
Yes, sir.
Rachel Olariwaju, where are you joining us from?
Akure.
Okay. Chebong Namtip, where are you joining us from?
I'm from Just Study Center, sir.
Okay, I thought as much. You're welcome. Ifi Joseph, where are you joining us from? Can you unmute yourself? Ifi Joseph, can you hear us? Ifi Joseph, can you hear us? If you can hear us, you need to unmute yourself and say something. Oifweme Friday, can you hear us as well? So you're welcome to PHY 203 class. Okay, Ifi Joseph said she's from Abuja. She's from Abuja. So you're welcome to PHY 203 class. This will be an 8-week event whereby we will go through the course outline. So what will happen is that I will be telling you what I hope you've all downloaded the course material.
Yes, sir.
Okay, give me a minute.
Yes, sir. We are still on.
Okay. Please, can you open your material?
Yes.
Okay. Okay. Um, So have you seen the lesson plan? Can you actually bring out the course material? I want us to open it. This class we hold every Monday. How many of you are taking PHY 207 as well?
Hi,
Yes. I'm taking it, sir.
Okay.
I'm taking it too,
Virtually,
sir.
virtually everybody here, right?
I'm
Yeah.
Also
taking
taking
it,
PHY 203. So we'll be taking that tomorrow. I'll send the link. I'll send the link after this class to your various emails, just like the way I sent this. So I will want us to be reading, because the reason for online facilitation is for you to read up and come to the class. When you now come to the class, you will be able to, can you see the slide?
Okay.
So my name again is Alukutaiwo Joshua. Joining you from Abeokuta, Ogun State, Nigeria. So for today's class, we'll be looking at simple harmonic motion. Hey, please, can that person mute herself so that you won't disturb others? If I asked you to talk, that's when I want response. Hey, who is that? Someone should please, who is that person? I don't want to mute everybody, but at the end of this lesson, students should be able to, can you see the screen? Can you see the screen?
Yes, sir. We are seeing it, sir.
Okay. Okay. Let me read out something too. Please, who is that is having a chicken at the back of his or house? The person should mute.
Okay.
I can actually trace the person, but I'm sure, and if I will just send the person out of the.
Okay.
I'll just. So for week one, you can write down. For week one, we'll be looking at simple harmonic motion. And you are to read ahead of the class. Hey, who is that? Let me go back. Let me unshare this. I will see the person. I'll meet everybody now. Are you sure it's not from you? Man from Plateau State. Okay, I said the first topic here is a simple harmonic motion.
I'm not the one who is saying Richard.
No, I didn't say Rachel. I said the man from Jos.
Okay.
So from the first topic is simple harmonic motion.
Okay.
The second topic will be superposition of harmonic oscillators. The third topic that I will take in this class will be damped harmonic motion. Then number 4 will be forced oscillations and resonance. Number 5 should be coupled oscillation. Number 6 will be wave motion. Number 7, waves at the boundary of two media. Then for the last class, we have a superposition of waves. So the course material will be our guide all through, in which I'm trying to open the course material now. I hope you have it there. Let me return this back to the screen, share screen. I guess you can see the slide now. So the first topic there, I will just talk briefly on it. So, and you go and read up, then you read ahead of the class, because coming to class is just for us to bring questions to class, and throw more light to it, and before you know it, we are good. And you can see that, are there anybody repeating this course? I doubt it, because we were able to look at this course very well, in depth. So there was no issue with anybody repeating this course. So in classes like this, we can only explain a few things. So you have to go back and study the material on your own. Then, if you are having issues with anybody, with any of the questions, that's when you can revert back to us. I want us to quickly do something. How many of us are here now? We're about 8. I want everybody to go to, let me stop share. I want everybody to go to the chat and drop your phone number. So I want Divine, I guess you can hear me. Divine, unmute yourself, I guess you can hear me. Divine, can you hear me? Unmute yourself. If you can hear me, can you wave your hand? Divine. Divine, can you hear me? Divine, can you hear me? Okay, Divine can't hear me. So I will have to give the assignment to Rachel Olarewaju. Rachel, what you do is that we are dropping our numbers here. Try to
Okay.
copy them out and you form a WhatsApp group. You call it
Okay.
PHY207.
07.
PHY207 2022 class.
Okay.
You add everybody's number to it. So that
Okay.
is where we'll be having a daily interaction.
Okay.
You get that, right?
Yeah,
Send
got
my
it.
number now. I guess everybody must have. Someone is saying, Kevin is telling Rachel to go and kill that fowl. I guess Rachel will share.
I'm not the one, yo. No,
Yeah,
I don't have
okay.
far around.
So you're Kevin, she is not the one, but someone is
I'm not.
interested in that fowl. So,
Mm.
definitely. So the class should be a kind of interactive class. After online classes like this, we can still meet again. By the time we go through the course material and you're not clear with one thing or the other, you can easily revert back to me while
Okay.
you can revert back to the group, you drop your questions there and everybody will treat it. Then I'll give my final verdict. So is that clear? Do you have all the numbers now?
Yeah.
Okay. So we're expecting your message. So I said from the first topic, I said simple harmonic motion. Unit 1 will be for today. Anyway, we stop. I have a summary that I'm going to present to you now, about 12-page slide. Then for next week, so you have to read all the way from page, according to the material, page, it is 5 of 237, from page 5 of 237, but it is numbered page 140. So you read from 140 to up to, what's it called? Let me see. You have to read up to the end of, I'm coming. Let me see the lesson plan again. Let me see what that covers and where that stops. The lesson plan is on the course page. So if you go to my dashboard, the dashboard for this course on the eLearn platform, the course outline is there. So you are to read the whole of unit 1, which runs from page 140 to come here, I'll tell you the page now. To 1. I'm almost there. Okay. So it will be from page 140 to page 1. To page 1. Let me see the page 140 to 150 to 172. 140 to 172. Is that clear? Hello?
Yes, very
Okay.
clear.
To 172.
Yes, it's clear, sir.
Which one? So I'm coming. Okay. So you do that. So no, to 171 actually, sorry. It's 171, 140 to 171. So that is the summary of, I'll give the summary now of all that now, 140 to 171. So you have to go back and do the necessary, do the needful in that case. Is that clear?
Yes, sir.
So now let's go to the business of the day. I said intended learning outcomes. So that's for learning outcomes. At the end of this lesson, students will be able to state the basic criteria for simple harmonic motion of a system, establish the differential equation for a system executing SHM, define the term amplitude, phase, and time period, compute potential, kinetic, and total energy of a body executing SHM. Is that clear?
Yes, sir.
Also, please inform others as well that the class has started. If you have people that are taking this course, inform them as well. So deduce the expression for average potential and average kinetic energies and discuss their significance. Now let's go to the fourth slide here. It says simple harmonic.
Sorry, sir. Please, can you share your screen so that we can see?
Oh, I think I'm sharing it. Okay, let me show
No,
you. Oh, sorry about that. I was sharing it until we. Adam Ahmed, you wanted to ask this question?
I don't know. I'm just asking you to share your screen.
Okay, sorry about that. I thought I was sharing it before. Can you see it now?
Okay. Okay. Yeah. We can see it now, sir. Thank you very much.
Good, thank you. Thank you for calling my attention. I like that.
Thank you.
So I read before. Come in. Let me see if this one will be much more clearer. I think it's much more clearer now.
Yes.
Good. So at the end of the lesson, students should be able to state the basic criteria for the simple harmonic motion of a system, establish the differential equation for a system executing SHM, define the term amplitude, phase, and time period, compute potential, kinetic, and total energy of a body executing SHM, deduce expression for average potential and average kinetic energy, and discuss their significance. Now let's go to the next slide. What is simple harmonic motion? We said, so we start with the word oscillation. So we said oscillation can be described as the back and forth, that's the to and fro movement of an object. And we said that since such a motion, can be represented in terms of sine and cosine, it is called an harmonic motion. And what do we mean by that? The word sine and cosine. You know, when we talk about graphs are especially graphs that are going up and down. I want to unshare this. I want to show you something. Let me unshare. I want you to look at my hand. I want to demonstrate something. Now, if you have a graph, can you see my arrow? The arrow of my laptop. Can you see my hand?
Yes, we can see.
Now, let's assume you have an X and Y plane. Is that clear? Now,
Yes,
we have a graph that starts at the origin. You know the origin? The origin is a point whereby the X and Y axis intersect. Is that not so?
Yes.
So any graph that starts from there and goes up and down and goes up and down, that's a sine graph. But if a graph starts at any arbitrary point, probably from the x-axis down, up, down, that's a cosine graph. Can you draw that out now? As we proceed, we will see different graphs. So, and such movement can be, they are what we call sinusoidal movement. Up and down movement is called a sinusoidal movement. So we said examples of bodies, and it is called harmonic motion because they follow a particular pattern. Exactly. It goes up and it comes down. It goes up and it comes down. It is harmonic. It has harmony. Is that not so? That's why it is called harmonic motion. Now, we now see the different bodies that perform oscillatory motion. So the first example there that we can see is the oscillation bulb of a pendulum clock. Have you seen a pendulum clock before? Have you seen a pendulum clock before?
Yes,
Yes, it moves to and fro.
and fro.
Yeah, that's a body performing oscillatory motion. Please, if you are the one, Ahmed, I guess you are the one having a background. Please, can you mute yourself? Ahmed, please mute yourself. Now, another example is the piston of an engine. If you see an engine move, the piston moves up and down, up and down. So that's another oscillatory motion. The vibrating strings of a musical instrument, that's another one. The oscillating uranium nucleus before it fissions, that before it splits. So that means an uranium nucleus. If it is oscillating before it splits, that is another example. Even large-scale building and bridges may at times undergo oscillatory motion. Now to the next slide. Come in. Now, let me go back to this form. Why is this thing closing? Can you see it again? Can you see the slide again?
Yes.
Good. So now to the next slide. I think I will leave it this way. So to the next slide, it says oscillation of a spring mass system. Now, looking at this, please look at these figures A, B, and C carefully because it will form the basis of this topic. We have a spring and a mass system. Now, a spring mass system consists of a spring of negligible mass. So we are not considering the mass of the string whose end is fixed to a rigid support. Can you see the rigid support on A there? Rigid support, and the other end carries a block of mass M. Can you see? We assume that the surface is frictionless, so we are not considering the force of friction acting on it. Now, at point A, this is a point where the spring is neither stretching or compressing. That means it is at rest. Nothing is happening to it. This is the equilibrium configuration, where displacement from that point is equals to 0. Now, if you look at it, there is no form of displacement. Is that not so? Is that not so?
Yes.
Displacement is 0. We are still going, you see all this, the practical application of all this very soon. Now, look at B. There is a kind of extension. That means the mass, the block, has been moved from its original point forward to another point, which is that X is now greater than 0. And the third one showing compression, in which also the mass has been displaced, but it is compression, which is such that X is now less than 0 with reference to where it starts from. Now let's look at the next slide. Note all this. Said the more you stretch or compress the string, the more will be the restoring force. So the direction of the restoring force is always opposite to the displacement. And if you look at it, we still go to the mathematical expression. I think I have it somewhere in the next slide. So if the total change in length is small compared to the original length, then the magnitude of restoring force is linearly proportional to the displacement. So what we are saying here is that mathematically, that obeys Hooke's law. What do we mean by this statement? That if the total change in the length is small, that means it can still be restored. Is that not so? It's not overstretched. Is that clear? And it can go back to its original length. The magnitude of the restoring force is proportional to the displacement. So we are saying that F is directly proportional, proportionality sign. You can write down to X. And the negative sign there is showing that it is in the opposite direction. So when a body is stretched in the right direction, it restores back in the left direction. Is that clear?
Yes, sir.
Good. So that is why, so it obeys Hooke's law. That's why we now have the K is a constant. So F equals to minus Kx. So you can calculate the extension. If you have the extension, you can calculate the restoring force. K is a constant. So we said the negative sign signifies that the restoring force opposes the displacement. Can you see that? The restoring force opposes the displacement. That means F is opposite that of the displacement X. So we also said that the restoring force is always directed towards the equilibrium position of the oscillating body. Can you see that? We said the restoring force is always directed towards the equilibrium position of the oscillating body. Now to the next point. These are the highlight of the note. So for a body to undergo SHM, the following conditions must be satisfied. One, we said that the restoring force is linearly proportional to the displacement of mass from its equilibrium position. It's just restating this F equals to minus Kx, and also the restoring force is always directed towards the equilibrium position. Now, going to the next slide. Now, we now said we want to calculate the velocity and acceleration of a body performing SHM. Now, frequency, we want to define, we are trying to define some times there. We said frequency is the number of oscillation per second in the SI system. Now, let me throw light to something. You know, if you are performing a simple pendulum experiment, you know, we use stopwatch, whereby we note the time it takes for a certain number of oscillations. Is that not true? Is that not true?
Very true.
So for a body performing SHM, we can say we want to know the number of oscillation in 20 seconds. So to get the period, it will be the period capital T stated there will be N divided by T, which will be small, a number of oscillation divided by the time taken for the oscillation. Is that clear? So the capital T there is N over small t. Is that clear?
Yes, sir.
Good. So N is the number of oscillation.
Chance.
We said in simple SHM, the displacement x of t from its equilibrium position is described by the equation x equals to x of a given mass cos omega t plus phi. Please note that for a body that is performing SHM, the equation, the generalized equation is given as that, in which xm is the amplitude of the displacement, y wt omega t plus phi is the phase transition, is the phase of the motion, and phi is the phase constant. By the time you check examples, you understand this the more. So in cases like this, this is the displacement. You know, in normal linear equation, we have velocity to be displacement over time. Is that not so?
Yes.
Or when you differentiate displacement, you get velocity. When you get velocity, you get acceleration. Is that clear? The same thing is applicable here. Now, this is the displacement equation. Now, when you differentiate this, the x, the t, will give you this equation here, which is omega. If you differentiate omega, we come out from here. Cos theta will give you minus sine theta. That's why the sign minus sign here is here. Can you see where I'm pointing the arrow?
No.
Down the equation. We don't have
Okay,
much time
sir.
again because of the Zoom. It's limiting us, but we might actually reconnect if it cuts us off. So if you differentiate this, x equals to x m cos omega t plus phi, we said that omega here equals to 2 pi f or 2 pi over t. Can you see that?
Yes, sir.
Good. Now, if you differentiate this equation 1 here, it will be v. If you differentiate displacement or distance, it will give you velocity. Is that not so? So it will, if you differentiate, it will give you minus omega x of m sine. If you differentiate cos theta, it will give you minus sine theta. Is that not so?
Yes, sir.
If you differentiate cos theta, it will give you minus sine. That's why you have a minus here. Minus omega. The omega comes out because it's a function of time. You know, it is the x, the t. So it will be minus omega xm sine omega t plus alpha plus phi rather. Exactly. Which is velocity.
Yes, sir.
And you know, the acceleration is a second order derivative. So if you do repeat the same thing with this equation, velocity to get acceleration, it will be minus, it is still sine theta. If you differentiate sine theta to give you cos theta, so it will not be a negative value. It's still the negative value here, but this omega will come out again. So that is why it's giving us minus omega squared xm cos omega t. Now, that means what we have here is that means the acceleration is just that minus omega squared x. Is that not so? This x, everything we still have in this equation 1 is still what we have here. The only difference is just the minus omega squared. Is that not so?
Yes, sir.
Can you see that? The difference is just the velocity. Now, I'm just trying to throw your light to all that. Okay. Let me go to next. Note that the acceleration magnitude is 0 when cosine is 0, which is when the particle it has at rest position. So there's no acceleration for a particle at rest position for that first diagram we have there. A, can you remember?
Yes, sir.
Good. So we said acceleration magnitude is maximum when the cosine magnitude is also maximum. So which is when the particle is at the extreme point, exactly the maximum point, where it has been slowed to a stop so that its motion can be reversed. So A is just a function of minus omega x of t. Is that clear? So in SHM, the acceleration A is proportional to the displacement, but opposite in sign. Is that also is acceleration here, A, small a here, is directly proportional to what? To displacement x of t, but with a negative sign, and the square, and is related to the square of the angular velocity. Is that clear? This angular velocity or angular frequency. Now, there's a summary of a table here. Now look at this table here. This table here is showing us bodies that perform simple harmonic motion. Now look at the spring mass constant. It's giving us this. If you want to find the differential equation, by the time you go through the material, you understand this better. So the inertia factor is m, the spring factor is k, the W naught is k over m, the period of oscillation is 2 pi m over k. Now, for a spring mass body, this is the differential equation. You read through, when you read that material, you will understand. For a simple pendulum, it gives this, and these are the summary compound pendulum, and it's like, you know, this online class is not as if we have to come to class and explain everything. So let's look at this. Let's look at this slide. We can apply Newton's second law to describe the force. Now, we've been able to talk about the velocity, acceleration. We want to talk about the force now. Is that not so? And we know that F equals to ma. So we're just trying to reintroduce the m multiplied by a. And our a here is what? Minus omega squared xt. Is that not so?
Yes,
So F will be minus m omega x, omega square x. I guess you can all hear me.
yes, yes.
Yes. So that is what this means. That means for a force, for a body performing SHM, the force is also F, which obeys Newton's law, equals to F equals to ma. So it is A, and A is minus omega squared x. So the m is just introduced. For F, now look at these deductions. But we said F equals to minus kx from the first equation we have. So if we impute the value of F into this equation, now this knocks out this x knocks out the x here. So k will now be m omega squared. That means this one now gives us a suitable what's called formula for omega, which is the angular velocity. So period t will now be, you know, we said t equals 2 pi over omega. And if you put omega here, it will turn. M will come up, k will be down. So this is a summary of what we have. In our next class, you can look at this class activity. You can quickly take a screenshot of this question.
Okay.
I quickly do that.
Yeah.
Something might go off at any time. So we'll continue on the WhatsApp group. Take a screenshot of this question. With what I've said so far, you should be able to solve this question. And next week we start from here. So it's nice meeting all of you.